Fort Worth Astro
Good
account up
evening,
and running.
everyone. My name is Bruce Campbell, and I'd like to start the general meeting for July 2025. This is the Fort Worth Astronomical Society, and we have a great show for you tonight. I think you'll enjoy it. Let's go to the next slide. So we're working on it right now. There we go. So do we have any visitors who are joining us tonight? No, that sounds good. Well, I see that Maru, the chair of the membership committee, is with us tonight. Hi. Yeah, stand up. I think that'd be great. There you go.
Some of you may not know me. My name is Maru. I've been doing membership coordination for quite some time. Thank you. I see some of you in the start audience, but you don't know me. My name is Horst.
Yep, thank you. And Maru came to the meeting equipped with clips for your badge. So if you have a badge that's currently clipless, we have them up front. And we'll have them here for each meeting. So new members need to come to the meeting, at least one meeting, to get a clip for their badge. All right. Okay, let's go to the next slide. Well, hey, these are our new members since we last met. Are any of these folks with us tonight? Oh, very good. What would...
I was actually a member like 2 years ago, just for a little short while, and I went back to New York, but now I'm back. So this was the first visit.
Very good. Tell us what you want to get from the club. Could you tell us what you want to get from the club? How can we help you?
I'm dying to see the new space out in the dark sky space.
Yes.
It was like just the beginning rumor back 2 years ago, and then sell my way through it. So.
Okay. Well, what I encourage you to do is join the e-group for the to share that information. If there's a weekend that you want to go, make a post, and there will be probably several people who will say, I'll meet you at a certain location, and we'll either carpool or caravan out there, and then you can get the lay of the land. That sounds good. Welcome.
And for what it's worth, I'm out there almost every week.
Right. So there's...
I don't know if all the work is done or not. I mean, last month, you guys were still talking about there was still some stuff that you were doing. So my weekends are free. So
Okay. Okay.
One other thing, if you use GPS, it will stop you short.
yeah, I saw that.
Like 4 o'clock.
I'm like, I don't want to go alone anyway. So.
Okay. So some of the comments from the group to Madeline, is that correct? Or which one are you? Madeline. Jane? I'm Jane. Okay. For Jane was, there's usually somebody out at the dark sky site each weekend doing some work, needed work, necessary work at the site. I didn't realize I was going to be tested on this. The field is groomed. It's mowed frequently. We're falling behind with the rains and the weather, but we'll catch up. And there are pads that you can use and set up your equipment so you're on a flat level surface. And something that wasn't mentioned, there's a good chance you'll be visited by one of 2 dogs or maybe both dogs. And they are, most part, they are very friendly, and they will bark at things in the night that you can't see, so they're defending your presence. Is that close enough? Good enough? Oh, a recommendation to take earplugs because the dogs will bark in the middle of the night. Okay. Next slide. Okay, a little bit about our society.
Most people think they know same.
We were founded in 1949. We have 173 members right at this point. And you'll see we have 30-plus people here with a wide range of experience. If you have an astronomy question, one of these folks can most likely give you an answer because they're always willing to help. And it's worth pointing out we're a 501(c) organization, so we can take charitable donations, and you can always take that off your taxes, especially in the years to come. I'll go to the next slide. So in terms of our resources, we have a member handbook, and that's for the most part, that tells you how to behave at a star party, as well as some good information about what to do in and around club facilities. The next item is we have access to the Thompson Observatory. Let's go to the next slide. And this is the observing area that we were talking about earlier. We've done quite a bit of improvement since we purchased material in 2002. We have pads, buildings, compostable, not combustible toilet, but a compostable toilet. There you go. But you're more than welcome to come out and visit. So good. Let's go on. We do have, the club does have telescopes and eyepieces for people to check out these type of equipment. We're more than happy to loan it to you, and so you can check it out before you buy a similar type of equipment to see if it's the right fit for your gear. Okay, next slide. And then in terms of FWAS things online, we have our website, our Facebook account, our YouTube, where we keep recordings of the meetings and special events. We also have 2 email exchanges. One's the group that I mentioned earlier, and then we do have an astrophotography special interest group, and so those are emails that circulate within that group. I did want to point out we do have a Zazzle account where you can get nice FWAS bling, and that's cool. There's a variety of shirts and cups and other things that advertise the club. All right, let's move on.
Thank you. So I wanted to introduce Dr. Sarah Horst. She's an associate professor of Earth and Planetary Sciences at John Hopkins University, and after she graduated, she actually worked at JPL, where she was on a team of people that analyzed the Cassini-Huygens images. And now she's on the engineering and science team for the Dragonfly mission, which is set to go to Titan. She's a big Titan enthusiast. She studies atmospheric chemistry. And so please help me welcome Dr. Sarah Horst.
All right, can we hear me? That's going to be step 1. Yes, no. Can you hear me?
I can hear you.
Okay.
Yeah, online can hear you.
Hopefully the people in the room can hear me too. Otherwise, it'll be a cozy little group tonight. Okay, and then the next step is to get my slides to share correctly, which seems like it's working okay. Can you see my slides all right? Online
Yes.
people can. Do we have any confirmation that the people in the room
Yes.
Oh, yes, sorry.
Okay.
I'm holding all the microphones. Sorry about that. Yes.
No worries. Just wanted to double check. Wouldn't be great if the people in the room were missing out. Okay. Let's talk about Titan. Thank you so much for having me. It's always really fun to talk to groups like yourselves. I think it's really fantastic that people, as kind of an amateur or semi-professional thing, are so excited about astronomy that they kind of do it as their hobby. I do not do it as my hobby. As it turns out, I am lucky enough to get paid to do this. But tonight what I'm going to talk to you about is Titan. I think we established that already. I apologize in advance. There's a lot of dogs happening in my life right now, which is the danger of doing these things from home. So if weird things seem like they're happening in the background, it's related to dogs, which it sounds like you guys have some experience with. Um, so I'm going to talk to you about Titan tonight, and what I want to kind of tell you the story, or how we're going to frame the story, is kind of what I consider the job of a planetary scientist. And so we take those points of light that you all see with your telescopes when you look up at the night sky, or even with the naked eye, depending on what object you're looking at. And we take those points of light and we turn them into objects that we study with all of the same tools that Earth scientists use to study Earth. And so we're taking these points of light in the night sky and we're turning them into worlds that we really think about in the same way that we think about Earth. And in doing so, really try to answer some of the biggest questions that we have about our own planet, about ourselves, about the universe. And so that's kind of how we're going to frame the story tonight. If I can get my slides to advance. There we go. So for Titan, that story starts in 1655 when Titan was discovered by Cassini-Huygens. He was looking at Saturn every night, which hopefully most of you have done. Saturn is spectacular through a telescope. And of course, at the time, the telescopes weren't so great. And so through his telescope, Saturn kind of looked like a dot or a circle with ears. And then he noticed that night after night as he was looking at it, and this is the drawing that's shown in this book, that there was this point of light that was moving. It was changing its position every night. And he was smart enough to recognize that this meant that this object was in orbit around Saturn, and that this was a moon of Saturn, and presumably a very large moon to be able to see it with this type of telescope. So that was 1655. And then basically nothing happens for like 250 years. And the reason for that is that, Saturn's pretty far away from Earth. We were really waiting for telescopes and the ability to make really robust and accurate telescopes. We were waiting for the technology to catch up. So the next thing that happens is a little bit debated. But in 1907, there were some observations that were made from an observatory in Barcelona. And the part of this is kind of controversial, is that when looking at Titan, it was claimed that they saw evidence of what's called limb darkening. And limb darkening occurs when you're looking at a planet or a moon that has an atmosphere, because light interacts with, kind of the solid surface. So the thing where the photons are just going to run smack into a solid and they're not going to be able to pass through. It interacts with the solid surface very differently than it interacts with the edges of the planet, where you're actually only seeing through atmosphere. You're not seeing the solid surface. And so when you see limb darkening, usually when you're looking at an astronomical object, that's pretty indicative of it having an atmosphere. He does not get credit for discovering Titan's atmosphere. There's a lot of debate about whether or not this would actually be possible, this observation would actually be possible using the telescope that he was using. But I think, as probably some of you know, when you're using some of these smaller telescopes, and especially back in the day when the lenses weren't so great, your own personal eyesight actually mattered quite a bit for how good the observations were. And apparently he was known to have quite good eyesight compared to most, people at the time. And so there's debate. Did he see limb darkening? Did he not see limb darkening? We're not really sure. I will say, this was 1907. We did not get the actual answer to the question for almost 40 more years, which is kind of crazy to me. So the next step in our journey from turning Titan, from this point of light that Cassini-Huygens discovered, into a world that we study like we do today, was in the mid-1940s. So Gerard Kuiper, who everyone probably recognizes the name from the Kuiper Belt, which is named after him, was doing spectroscopy of Jupiter and Saturn, and then the 4 Galilean satellites, so Callisto, Europa, Ganymede, and Io, and then also Titan. And one of the things that he noticed while he was doing spectroscopy, he was looking in the infrared, was that there was a spectral signature that was shared by both giant planets. So Saturn and Jupiter both had this spectral signature, and Titan also had it. Callisto, Europa, Ganymede, Io, nothing. That spectral signature was methane. And so Kuiper wrote a paper that was called Titan, a Satellite with an Atmosphere. I've always felt like this title is missing some kind of punctuation. It needs an exclamation point or a question mark or something, because this is very bizarre. And we're going to delve more into that momentarily. But Kuiper is the one that's credited with discovering that Titan has an atmosphere. He discovered that there was methane surrounding Titan, and that kind of was our first inkling that Titan was going to turn out to be a really interesting object to study. So the reason that this is so interesting, I think, is summarized really well in this infographic that was put together by Emily Lakdawalla when she was at the Planetary Society. And she calls this her collection of the not planets. So these are all of the objects in the solar system that are round, but are not planets. Most of them are not planets because they're moons. Some of them are not planets because they don't clear their orbit. But all of these objects are not planets. And Titan is sitting in the middle, being super weird. So if you look at all of the other objects, and I wish that she had updated this infographic, you can kind of tell how old it is because the Pluto and Charon images are so old. But if you look at all the other objects in this image, you see their surfaces. You see, these big impact basins on Ganymede or on the moon. You see, the fractures that are so characteristic of Europa. You see the volcanoes on Io. And you look at Titan and you see...
We lost audio.
Uh-oh. What about now? Yes, no, maybe?
Online, you're still good.
Okay.
I never lost you.
Yeah, I'm still
Yeah, we're good.
Okay.
Must be me.
It happens. So Titan is super weird. It has this atmosphere. It prevents us from seeing down to the surface. And so, kind of immediately, just looking at this infographic, something really interesting is happening here, and you should be asking yourself a lot of questions, which we are going to get to and spend kind of the rest of our time together talking about. So 1944, Kuiper discovers methane. Titan has an atmosphere. Now what? Basically nothing. Again, we're just constantly waiting for technology to catch up with our questions. I think it's one of the frustrations of being a scientist, actually, is constantly waiting for technology to catch up with the questions that we're able to ask. And so our next big step in understanding Titan came not with a telescope, but with a spacecraft. And so in the early 1980s, Voyager 1 and 2 flew through the Saturn system and returned images, spectacular images of the Saturn system, including this maybe less than spectacular image of Titan. I always like to joke with people that you can recreate the Voyager flyby of Titan in the comfort of your own home with an iPhone and an orange. You'll get a much higher resolution image that contains approximately as much information as this picture did in terms of what is going on Titan. Luckily, we weren't only going to be tortured by this image. Voyager was also carrying an infrared spectrometer, and so you'll notice a trend here that we like to use infrared light to study planetary atmospheres, the same way that Kuiper had discovered the methane. We're able to characterize Titan's atmosphere using infrared light. This spectrometer, called IRIS, discovered a bunch of molecules that we did not know were present in Titan's atmosphere prior to Voyager. And so if you have not taken chemistry ever, or maybe it's been a very long time, you'll survive this talk. Don't worry, I promise. But some of the molecules that Voyager discovered, you are personally familiar with. So for example, there is propane. So if you want to have everybody over to barbecue for the weekend at your house on Titan, you will be fine. There's propane on Titan. There's acetylene if you are interested in welding. There's a molecule called ethane, which you're probably less familiar with. There's also hydrogen cyanide. So if you were going to invite everybody over for the weekend, but you don't really like your friends and family that much, you have the opportunity to poison them if you so desire. But the point was that we had this moon. It has an atmosphere that's really weird. It's the only moon in the solar system that has an atmosphere. We cannot see the surface. There could have been 12-foot Titanians jumping up and down and waving at Voyager as it flew through the Saturn system, and we would not have known. And then it turns out that Titan's atmosphere is full of organic molecules, and we're going to talk about why that's interesting more momentarily. So just to give you a little bit of context and step back a little bit and just kind of summarize a couple of things that we know. Titan is the largest moon of Saturn. If you're looking at the image in this backdrop, you're telling me that that is Saturn, not Titan, Sarah, and you're right. Congratulations. Titan is, if you can look down at the bottom kind of middle to the right of your screen, there is a little orangish ball down there, and that is Titan. So you get a sense of scale with the Saturn system. It's the largest moon of Saturn. It has a diameter of about 5,150 kilometers. It's larger than Earth's moon. It's actually larger than the planet Mercury. It would be the largest moon in the solar system if it weren't for the fact that Ganymede is just slightly larger. If you include Titan's atmosphere, Titan's actually larger than Ganymede, so they're pretty comparable in size. It has a mass of about 0.0225 Earth masses. If you take that diameter and mass put together, you get a density of about 1.9 grams per centimeter cubed. That means that Titan is about half rock, half water ice. We know from subsequent spacecraft measurements that Titan is partially, if not fully, differentiated. So like the Earth, most of Titan's dense materials have gone to the center to form a core. In this case, that means that all of the rock, all of the silicates, all the things that we think of as rock on Earth have gone to Titan's center. And so Titan's crust is made out of water ice. The reason that works is that Titan's surface temperature is 94 Kelvin. I'm a horrible outreach person in this particular moment because I do not know what that is in Fahrenheit. It is so cold in Fahrenheit, it literally doesn't matter if I told you what it is because you have no personal experience with anything that is even remotely this cold. At this temperature, water ice behaves like granite. Titan's surface pressure is about 1.5 bar, so that's 1.5 times the surface pressure at sea level on Earth. And so, like I said, it is a substantial atmosphere. And again, it's the only moon in the solar system that has a significant atmosphere. And so right away, that is really interesting in and of itself. It may have been a while since you've seen a phase diagram. But just to orient you, the x-axis is temperature, the y-axis is pressure, and this is labeling the different regions that tell us what phase of matter these things are in. We might be used to looking at these for water here on Earth. Right now we're looking at it for methane on Titan. The little red T is Titan's location. Titan is located very close to what we call the triple point. So that is the place where solid, liquid, and gas can exist at the same time in the same place. If you remember any of your Earth science, Earth is located very close to the triple point of water. That is the reason why we have a water cycle on Earth, why it can rain and snow, why we have water vapor in the atmosphere. Those of us who live on the East Coast are very familiar with that happening all at the same time on the same day. It's something that we call a wintry mix. Don't think that you're as familiar with that phenomenon in Texas, but some of you probably have lived other places in the United States where you're exposed to that type of weather. And so Titan is very close to the triple point of methane, the way that Earth is very close to the triple point of water. That tells us, knowing nothing else about Titan, knowing none of the things I'm about to show you, that methane is probably cycling between Titan's surface and its atmosphere in the same way that water cycles between the surface and atmosphere of the Earth. And so that leads to the possibility that some really interesting things are going on. So I already mentioned that Titan has a dense atmosphere. We know there's methane. I told you that already. Kuiper discovered it. Methane turns out to be the second most abundant molecule in Titan's atmosphere. So it's about 2% methane. The most abundant molecule in Titan's atmosphere is molecular nitrogen. So it has abundance of about 98%. Molecular nitrogen, which maybe some of you know from doing your own observations, does not interact with light in any really interesting way. And so we're not able to use spectroscopy really to look for nitrogen in planetary atmospheres. And it's the reason why methane was the one that was first discovered, even though nitrogen is the most abundant. So I told you that Titan is the only moon in the solar system that has a substantial atmosphere. That makes it weird. The next weird thing about Titan is the only other atmosphere, the only other substantial atmosphere in the solar system that is primarily made out of molecular nitrogen besides Titan is our own Earth. So our own atmosphere is about 78% molecular nitrogen. And so immediately this tells us that we have a lot of questions that could potentially be answered about the Earth by studying Titan. And so that's one of the reasons why we're so interested in it. Now, we start with nitrogen and methane. We expose it to sunlight. Those molecules break apart. They react and make new molecules. The molecules get bigger and bigger. They form things called hydrocarbons, which is just carbon and hydrogen in a molecule together. They form things called nitriles, which is what happens when a carbon atom and a nitrogen atom bond together. They keep building bigger and bigger molecules until we get actual particles that form this kind of characteristic haze layer on around Titan, which is one of the reasons that we can't see down to the surface. You are, as a human being, very familiar with this process, although you may never thought about it before, because this is exactly how smog is made on Earth. By sunlight interacting with molecules that are emitted from power plants and from cars and from those kinds of things. Titan's atmosphere, in addition to everything that I just mentioned to you, also does have some oxygen-containing molecules, and I'll tell you why that's exciting momentarily. The three that we have detected to date are carbon monoxide, carbon dioxide, and water. Those are in decreasing order of abundance. So of those, carbon monoxide is the most abundant with an abundance of 50 parts per million. That doesn't sound like much, but that actually makes it the fourth most abundant molecule in Titan's atmosphere. And so why is this interesting? So backing up, talking about big picture questions, thinking about turning points of light into worlds, one of the big picture questions that we have is, how does life form? Is there life on other planets? In trying to answer this question, we think a lot about life on Earth. Life on Earth is based on a small set of molecules. So one set of molecules that we tend to think about are amino acids, which are the building blocks of proteins. Another set of molecules that we tend to think about are called nucleobases, which are the building blocks of DNA and RNA and some of our energy-containing molecules. That small set of molecules that all of life on Earth is based on, all of it, from the tiniest microbe living in the deepest cracks of some of the mines on Earth to, the largest animals that we see in the ocean or on land. Everybody shares the same set of molecules. That small set of molecules is based on a small set of atoms. The smallest set of atoms we think of as being important for that chemistry are carbon, nitrogen, hydrogen, and oxygen. So now I've just told you that all four of those atoms are present in Titan's atmosphere, participating in complex organic chemistry. So Titan is turning out to be a really interesting object in the solar system. So that's kind of where we're at. We, again, had to be patient, especially if you study the outer solar system. Patience is a virtue. So Voyager flew through the Saturn system in the early 80s. We see this really interesting chemistry. We can't see the surface. Scientists immediately are like, we have to go back to Titan. Let's go. NASA has a different definition of like, we have to and let's go compared to most of the rest of us. But in formulation in 1983 was the mission that eventually became the Cassini-Huygens mission. Cassini-Huygens was a joint mission between NASA and the European Space Agency. It launched in 1997. It was 7 years in cruise. So again, being patient if you study the outer solar system is really important. It arrived in the Saturn system in 2004. Actually, right around this time in 2004. It was mid-July in 2004. The Cassini was the probe, or the orbiter. Sorry, Cassini was the orbiter. Huygens was the probe. Huygens is, if you're looking at this image, the kind of circular gold disc that takes up a good chunk of the view of the spacecraft is the heat shield for the Huygens probe. The Huygens probe was released shortly before Christmas in 2004, descended through Titan's atmosphere, landing on its surface on January 14th, 2005. Just to give you a sense of scale, I always forget to point this out in this image, but if you look down towards the bottom of the image, you'll see a bunch of white things. Those are actually human beings in bunny suits getting the spacecraft prepared for launch. And so Cassini is about the size of a school bus. It's not like a cute little Mars rover, but it's the size of a school bus full of science. Cassini's end of mission was on September 15th, 2017, around 7 o'clock in the morning Eastern time, when Cassini was intentionally, it's very important to point this out, intentionally crashed into Saturn, both to let us do some measurements in situ in Saturn's atmosphere, but also to protect some of the moons of Saturn that we think have the possibility to harbor life, and so we don't want to contaminate them. Cassini carried 12 instruments, Huygens carried 6. They were a combination of remote sensing instruments, which are things that you all are very familiar with, so cameras, spectrometers, all those kinds of things, and then also in situ instruments, so things like mass spectrometers, plasma spectrometers, things that actually would ingest material from the system or from the target and measure it in the instrument. This is just a gratuitous pretty picture because if you're talking about the Cassini mission, you have to show pictures of the Saturn system. And so this gives you kind of, again, a sense of scale looking at Saturn. There's a few different moons in this image. Although if your laptop screen is anything like mine, you would be hard pressed to figure out if it was a moon or a smudge. And so maybe I should clean my screen off. I like to call this Titan's baby picture. This is the first picture that Cassini took of Titan. This was actually taken before Saturn orbit insertion, so it was taken in April of 2004. You can tell that it was apparently important to no one because nobody ever bothered to process this image. So Cassini's cameras did take better pictures, I promise. This is one of the last pictures that Cassini took of Titan, and we'll talk more about this picture momentarily. And then this is actually one of the very last pictures that Cassini took of Titan. So this was taken on September 13th, 2017. Because Titan is such a large object in the Saturn system, Titan was actually used to basically control the entire tour. So the entire 13 years that Cassini was in orbit around Saturn, they were using Titan to do gravity assists to change the orbit over time. And so that also meant that for the grand finale, for crashing Cassini into Saturn, there was one last very close flyby of Titan that finally put Cassini on that last collision course. Okay, we have to do a little bit more chemistry. So I already mentioned that we have this chemistry that's driven by light from the sun. It's primarily driven by UV photons. About 90% of the chemistry is driven by UV photons. About 10% of the chemistry is driven by energetic particles that come from Saturn's magnetosphere. But in the end, what happens is that methane that was discovered by Kuiper is destroyed. And the current abundance in Titan's atmosphere would be destroyed in about 10 to 100 million years. And so we have a lot of questions about how it gets resupplied over time. But the reason that is happening is that when methane interacts with light, there's two molecules that are made in general. One of the molecules is ethane. I mentioned that to you before, C2H6. When methane reaches Titan's lower atmosphere, the tropopause is 70 Kelvin. Very, 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 very few things, like you can count them on one hand, number of things are gases at 70 Kelvin, noble gases mostly. So ethane condenses at the tropopause and it goes on a one-way trip to the surface. Once it arrives on the surface, it never gets warm enough. It never gets enough sunlight to evaporate back into the atmosphere. And so it's trapped on the surface forever. Hydrogen, which is the other product of this reaction, has a different adventure. Because Titan is small, its gravity is about 1/7 that of Earth's, Titan can't hold on to molecular hydrogen. And so it goes off on adventure. So it escapes, goes off into the Saturn system to live its best life doing something else. And so in this way, methane is irreversibly destroyed over time. This is the simple version of the chemistry. This is the slightly more complicated version of the chemistry. Never fear, we are not going to talk about this slide. It's just to tell you, complicated things happen. Complicated chemistry makes complicated molecules. This is why we think Titan is so interesting. All of that chemistry results in making these molecules. So these are the 10 most abundant molecules in Titan's atmosphere besides nitrogen. We've talked about most of them already. Again, ethane, acetylene, propane. I always forget what C2H4 is, hydrogen cyanide. These are all being made by chemistry that is driven by light that's coming from the sun. We're almost done with the chemistry portion of this adventure. So the thing about Cassini is that it really revolutionized our understanding of Titan in basically every way you could possibly imagine. I'm going to talk about more of those ways in a little bit. But when we get to the Dragonfly portion of this adventure, it is going to be very important for you to understand the thing that I am about to tell you, because the thing that I am about to tell you is the reason that Dragonfly exists, the reason that NASA selected us, the reason that we are going to Titan. So I mentioned a whole bunch of organic molecules to you a minute ago. I mentioned some to you earlier. Prior to the arrival of Cassini in the Saturn system, the heaviest molecule that had ever been detected in Titan's atmosphere was benzene, C6H6. It has a mass of 78. So the mass spectrometer carried by Cassini, built, designed, developed, flown specifically to characterize the complex organics in Titan's atmosphere, was designed to measure the composition from a mass of 1, which is a hydrogen atom, up to a mass of 100. which is something like 7 or 8 carbon atoms, or maybe nitrogen atoms, depending on what the molecule contains. That was the extent of what we thought was so interesting that we would build an entire instrument just to study it. And so this is kind of what we thought the data would look like from that instrument, which is called the ion and neutral mass spectrometer. We were very, very lucky human beings because in addition to the ion and neutral mass spectrometer, which was specifically designed to study Titan's atmospheric chemistry, Cassini was carrying an instrument called the Cassini plasma spectrometer, which was not designed to study Titan at all. The Cassini plasma spectrometer was designed to study the energetic plasma in Saturn's magnetosphere. So it was supposed to be looking at things that were as exciting as electrons or protons, or if you got like really, really exciting, maybe some oxygen atoms. But the Cassini plasma spectrometer, which we shorthand we call CAPS, was on during Titan flybys. And kind of immediately, the CAPS team started kind of tracking people down at the hallways and meetings and being like, so when we fly by Titan, weird things are happening. And so my PhD advisor came home from a conference early in the Cassini mission, and he said, man, the CAPS team is seeing some weird things. And we're all like, okay, we'll define weird. So this is the definition of weird in this particular case. So we're looking at mass on the x-axis. The y-axis is just kind of number of things and various way to count them. This is a logarithmic axis, which is my favorite way to stress out chemists when I talk about Titan to chemists, because you never see mass spectrometer data with a log axis. That's just not how these instruments work. So what is happening here? Very high in Titan's atmosphere, 950 kilometers above the surface, there are extremely heavy ions in Titan's atmosphere, much more complicated than we ever thought basically possible to be present in a planetary atmosphere, period, end of discussion. Not just Titan, but like this is not something that had ever occurred to people could possibly exist. To give you a sense of scale, this is the heaviest molecule we knew about, the biggest molecule that we knew about in Titan's atmosphere prior to the arrival of Cassini. That's benzene. The thing I'm about to show you is not a real molecule. It makes chemists want to cry, but I had to make something that gave you a sense of scale, and so this is the thing that's a sense of scale. So that's how wrong we were about the complexity of the chemistry that's happening in Titan's atmosphere. This has really fundamentally altered our ideas about the kinds of chemistry that planetary atmospheres are capable of. It's really changed our ideas about the chemistry that might lead to the origin of life. And also then that means it's going to change our ideas about how we search for life elsewhere in the universe. So this was a really big thing. It was also a really frustrating thing. You are going to notice a theme, if you haven't already, that Titan does not like to give up its secrets easily. It's actually at this point kind of a running joke in the Titan community that Titan will always do the most to make it impossible to answer questions about it, and this was no different. This instrument was not designed to do this. We can't identify any of the molecules in these data. We know they're there. We can see that they're very heavy. We have signal up to a mass of 10,000, which is something like 700 or 800 carbon atoms, not 7 or 8 carbon atoms, which is what we thought before Cassini, but we cannot identify these molecules. So that sucks. But we can do other things, and this is something that my group does, so I'm just going to talk to you about it a little bit, especially because you probably don't hear from people who do laboratory work in astronomy very often. But one tool that we can use in our toolkit, since we're not able to actually analyze, to actually identify the molecules from the data, is we can do laboratory simulations of planetary atmospheres and look to see what happens when we do those experiments. And the way that we do this is we take simple, abundant atmospheric gases. So if we're running a Titan experiment, we'll use methane and nitrogen and probably a little carbon monoxide because we're interested in that chemistry. We expose it to an energy source. Just like the solar photons are driving the chemistry in Titan's atmosphere, the photons from my UV lamp in my lab drive chemistry in the lab instead. Depending on the conditions that you make, and certainly if you're using Titan conditions, this results in the formation of a complex organic solid. You'll notice that this one is suspiciously Titan color, and so that says something right away about what's going on in Titan's atmosphere. But then we can take that material and we can analyze it with whatever tool we want to. So we can look at it with a mass spectrometer in the same way that mass spectrometers have studied Titan and look to see what molecules are in there. When we do that, we find a bunch of molecules that are interesting for the search for life. And I know I told you that the chemistry portion of this was almost over, but I lied just a little bit. So when we look at this material, and this was a paper from when I was in graduate school, we find purine and pyrimidine bases. What are those, Sarah? Those are those nucleobases that I mentioned before. So the building blocks of DNA and RNA. So that familiar ATCGU that you might remember from school. We see those in this material. We also see the two smallest biological amino acids. So those building blocks of protein, glycine, and alanine we see in this material as well. These are just Titan atmosphere simulation experiments, but they give us an inclination that that there may be these molecules present in Titan's atmosphere today, that the chemistry that led to the origin of life on Earth, which we think is very similar to the chemistry that's happening on Titan today, is probably capable of building these molecules. And so we want to go study them and find out what's happening. Are we on time? Okay. So this is Titan again, which you probably figured out by now. But instead of the Voyager Titan, we're now looking at the Cassini Titan. So if you spend $4 billion on a spacecraft, you get a higher resolution fuzzy orange ball. It turns out that the Voyager color palette was skewed a little bit orange for a lot of objects. You've probably seen a lot of color corrections over, I would say, probably the last like 5 years as people have reprocessed some of the Voyager data. Neptune, for example, not so blue, which is a little bit of a bummer. Titan is more yellow than orange, as it turns out. The good news is that this time we came prepared. We learned our lessons from Voyager, and so we have a lot more tools in our toolkit to study Titan this time. So I'm going to walk you through some of the things that we've learned about Titan from Cassini before we jump into what our next questions are. So we've been able to study Titan's haze layers, so you can see that there's a bunch of structure in the haze. We know that Titan's haze is made out of all these organic chemistry words that I've been throwing around all night: hydrocarbons, nitriles, blah, 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 whatever. We also know that there is an active methane cycle that I alluded to before. We could guess that from our triple point information, but we know it for sure now from observations. So these are clouds at Titan's south pole. The clouds and rain are made primarily out of methane and ethane. Because of this particular group, I will mention that Titan's clouds were actually discovered using ground-based telescopes, not space-based telescopes or a spacecraft. They were discovered using a spectroscopic technique, and some of the largest clouds that have ever been seen on Titan were discovered using a 14-inch telescope in LA, and then followed up using Keck because you need to actually get the images to prove how big the clouds are. We can actually see down to the surface. So Titan's atmosphere is opaque at most wavelengths in the visible and infrared, but there are tiny windows where you can see through the methane and the haze particles, and we knew that both from Voyager and from Earth-based observations. And so Cassini's cameras carried specific wavelength filters to allow us to look down to the surface, and so that's what you're seeing now. Titan's surface is made out of kind of two broad scale materials. We call them the light stuff and the dark stuff. Their light stuff is probably water ice. So this is the image from the Huygens probe. The Huygens probe landed in what was probably a dried wash. You can see that this looks very familiar. I think it mostly looks like Mars, but there's definitely places on Earth that this looks like also. You see that they're technically cobbles, so they're about 10 centimeters in diameter. They look larger because they're sitting very close to the camera lens, actually. We think these are made probably out of water ice, but they've obviously undergone erosional processes, as evidenced by the fact that they're rounded. So we think most of the light stuff in this large-scale Titan image is probably just bedrock, which we think is probably water ice, maybe with a little bit of ammonia mixed into it. The dark stuff actually comes in two flavors, so I lied to you a little bit. If you're looking at the North Pole, which is up in this image, the dark stuff are actually extensive lakes and seas. So these data now are not an image, although your brain is trying desperately to make them into an image. These are actually Cassini radar data. And so the way to interpret radar data is that if something is dark at radar wavelengths, that means it's smooth at the wavelength of the radar. So Cassini's radar was 2.2 centimeters, and so it's very smooth at 2.2 centimeters. Extremely smooth. In fact, the only thing that is that smooth at 2.2 centimeters is a very, very like flat, boring liquid. And then if things are rough at that wavelength, then they show up as being these like brighter kind of colors in this image, I guess. And so what you're looking at obviously are large lakes and seas at the North Pole of Titan. They're kind of the scale of the Great Lakes here in the US. You can also see that there's lots of dendritic features, there's channels and rivers and all of these other things. And so these lakes and seas are made primarily out of methane and ethane. They're particularly interesting to us actually because this is a place where a lot of extra chemistry can happen. All of those particles that I talked about that get made in the atmosphere end up on the surface eventually. And so whatever is soluble will dissolve in the lakes and seas kind of by definition. And then there's the possibility for subsequent chemistry to happen there. But all the things that are insoluble will either end up kind of as like gunk on the bottom of the lake and sea, the kind of stuff that like you probably wouldn't want to squish your toes in because it would feel kind of gross. Or it might be like kind of scummy stuff that's floating on the tops of the lakes and seas, depending on things like density. So this is a place that we're really interested in being able to study. It has the annoying feature, which I've already mentioned, of being at the pole. The reason that this is annoying is that Titan is tilted. It has approximately the same axial tilt as the Earth. And so that means that there are large parts of the Titan year in which you cannot see the North Pole from Earth. Which means that if you were a person that wanted to send a spacecraft to the North Pole to go look at the lakes and seas, you will very quickly discover that there are decades in which you cannot do that because you cannot communicate with Earth when you can't see Earth from the pole. So that's a little frustrating. All the dark stuff you see in the North Pole, lakes and seas. The lakes and seas are mostly confined to the northern hemisphere at this point in Titan's history. We have evidence that in earlier epochs, there were lakes and seas elsewhere on the surface, but right now they're all at the North Pole. The dark stuff you see everywhere else, from the mid-latitudes in the south to the mid-latitudes in the north, dune fields. Extensive dune fields. It's one of the major features of Titan's surface. This is what they look like in Cassini radar. These dune fields are very reminiscent of dunes that we see here on Earth. In particular, they're very analogous, at least in structure, to the Namib Desert, to dune fields in the Namib Desert. And actually, members of the Dragonfly team are going there in October to do some field work. The thing that's weird, if you were paying attention earlier, I told you that all of Titan's rock went to its core. On Earth, our sand is just eroded rock. And so if you go measure sand on Earth, you will discover that it is made out of the same composition as the rocks that are most of the time pretty nearby. Titan doesn't have any rock. The sand particles, through processes that we do not understand, one of my grad students spent 5 years trying to figure it out, are made out of organic molecules that were made in the atmosphere. Somehow, sand-sized particles are generated, they get transported by the wind, and we have these huge dune fields. The last place that we're really interested in, and this is important for Dragonfly as well, are impact craters. And the reason that we're so interested in impact craters is because there is no liquid water on Titan. Again, remember, it is 94 Kelvin, water behaves like granite. And so these organic molecules have never met a liquid water molecule in their whole entire lives. When there's an impact on Titan, the top of the impact melt pool flash freezes because of the fact that it's 94 Kelvin. That immediately acts to insulate the impact melt pool. And so you end up with these kind of near surface lakes that are frozen over on the top, but are still liquid below, and they persist for tens of thousands of years. They have organics that were on the surface mixed in with them, so the organics are exposed to liquid water. When you expose organics to liquid water, you make a bunch of the molecules that life on Earth uses. That's probably not an accident. And so this is a place that we're particularly interested in studying to try to see how far the chemistry on Titan has proceeded and what it can tell us about the origin of life on Earth and the possibility of life on Titan. I'm going to skip through a bunch of slides so that we have time for questions and Dragonfly, except I'm not going to skip this one because if you've never seen this image before, today is your lucky day. I'm on a one-woman mission to make sure that all of humankind has seen this image. This is the first sun glint we have ever observed from another world. So this is the sun reflecting off a lake at Titan's North Pole. When the team kind of reverse engineered the spacecraft telemetry and all this stuff, they were able to figure out which lake this actually reflected off of. And as luck would have it, this lake had not been named yet. Lakes on Titan have to be named after lakes on Earth. And so the lake that this reflection came off of is called Jingpo Locus. That means mirror lake. So I just have to show you this. It's really the only point of this slide, but it still gives me goosebumps and I've looked at it a million times. Okay, so I've been mentioning life off and on a bunch of times, and now we're gonna go all the way in. As astrobiologists, as people who think about the origin of life, the search for life, we tend to think of there being a few key ingredients for life, and I've already mentioned all of them, so we're going to go through this very quickly. So we need energy. I think this is intuitively obvious. We have sunlight. Fantastic. We need organic material, so we need the building blocks of life. Our proteins, our cells, all of these things are all made from organic material. Titan has so much organic material, it's literally making dune fields out of it, so that is not an issue. We also believe that life requires a liquid. We tend to be very Earth-centric and thinking that water is the most important liquid. There is no water stable on present-day Titan's surface. However, Titan does have a subsurface liquid water ocean. We always forget to tell people that because we get distracted. So people are always talking about Europa's subsurface ocean and Enceladus's subsurface ocean. Well, Titan has one too. It just has a bunch of other things going on that get us distracted. And then, of course, as I mentioned, at various periods in Titan's past, whenever there were large impacts, there was liquid water available on the surface for periods of time. In addition to liquid water, though, and I've mentioned this a bunch of times already, we have this active methane cycle. And so we have methane that is stable on Titan's surface for long periods of time. That gives the possibility that if life has been able to figure out how to use a different chemistry, to use methane as its liquid instead of water, that it could use that as its liquid that's required for life. And so on Titan alone, we can study this chemistry that may have led to the origin of life on Earth, that could lead to the origin of life elsewhere, in the context of a place, a world that is doing all of these planetary scale surface processes, Earth-like surface processes. It rains, there's rivers, there's sand dunes, there's impact craters, there's rainbows, like everything that you think of as being a characteristic of Earth, of a planet that is active, that is doing things. It is also happening on Titan with all of this chemistry that we think might be important for the origin of life. So this is why we're so interested in going back to Titan. And so I told you we're turning, points of lights into worlds. And so what's our next step? So our next step is Dragonfly. Dragonfly is a mission to explore Titan's prebiotic chemistry and habitability using a mobile platform. I should be immediately ejected from the Dragonfly team because this is a very old rendering at this point of Dragonfly because I haven't updated my slides in a while. But I'll show you the Dragonfly website at the end and you can go see some newer, prettier renderings that are more true to life for what's actually going to happen. So basically the deal with Dragonfly is that we're going to use a rotorcraft lander to do in situ investigations of Titan's prebiotic chemistry and habitability. In a lot of ways, we are very similar to a Mars rover. We carry a bunch of instruments. We're like a mobile laboratory. We're going to go to a site. We're going to investigate it for a while. The main difference is that when we want to go on to our next adventure, instead of driving, we're going to fly. And the reason for that is that Titan's gravity is 1/7 that of Earth's, and its atmosphere is 4 times denser. It is so much easier to fly on Titan than it is on Earth. It's almost a crime to send a spacecraft to Titan that doesn't take advantage of it. If you were standing personally, you yourself, on the surface of Titan, and if you find yourself in that situation, please call me. I have so many questions. But if that were to happen and you had brought like rudimentary wings with you, balsa wood or cardboard or something, and strapped them to your arms, you could flap your wings and fly. under your own power. It is that easy to fly on Titan. And so we're going to take advantage of that and allow us to access all of those diverse settings that I was talking about before. Okay, Dragonfly has 3 big picture science goals. These are not going to be a surprise to you after listening to me talk for the last like 40 minutes. So we're going to look at the prebiotic chemistry. We're going to analyze chemical components and processes that are at work looking for these biologically relevant compounds that I've now mentioned a bunch of times. We're also going to study the habitable environments on Titan. We're going to measure things like atmospheric conditions, look at how methane is transported between the surface and the atmosphere. We're also really interested in understanding processes that mix organics with water, liquid water, for all of the reasons that I already mentioned before. And finally, although I am contractually obligated to tell you that that Dragonfly is not a life detection mission, because it is not a life detection mission, we will search for biosignatures. So while we are there, while we are studying this complex chemistry, we will be keeping our eyes open for chemical evidence of water or hydrocarbon-based life on Titan. Our landing site is an impact crater. So this is Salt Crater, and this is where we'll be going. The reason for this is this gives us access to a bunch of those different areas that we're interested in, but particularly gives us access to organics that have mixed with liquid water in the past to study that chemistry that we're really interested in. We'll be landing to the southeast of Selk because we don't have like super high resolution imaging like we have of Mars. Landing is going to be probably the most dangerous thing Dragonfly ever does. Because that's the only time we're ever going to land without having imaging data first. And so we're sending ourselves to an interdunes region. Interdunes regions, just based on physics, tend to be very flat and evenly size sorted. There's actually a picture of an interdunes region on Earth in the bottom right of this slide, and you can tell it's Earth because there's people on it. But just to give you a sense of how boring interdunes regions are, that is an example. And so that's where we're going to be sending the spacecraft. And then we will start flying towards Selk and towards those other areas that we're interested in. I'm going to skip this one. We're carrying a bunch of really powerful instruments. So DRAMS is our mass spectrometer. That's really going to be our workhorse instrument. That's going to be telling us all about the composition that we're really interested in studying. To do that, we have something called Draco, which is the drill for acquisition of complex organics. And so Draco is a drill. It's mounted on one of our legs. And it will actually, hey, no, stop. They don't want to hear from you. The drill is mounted on one of the skids, and it will actually drill into the near surface and ingest material directly into the mass spectrometer. And so that's how we'll be able to get our samples into the mass spectrometer and do all this really interesting chemistry measurements that I have been talking about. Another one of our instruments that's going to give us some chemical information is called Dragons. It's a Dragonfly gamma ray neutron spectrometer. DRAMS is my favorite instrument because I am a mass spectrometry expert. But Dragons is my favorite named instrument because we get to talk about dragons on Titan. And Dragons is really nifty because using this gamma ray neutron spectrometer, we get bulk composition information just by sitting at our landing site. And so Dragons will be able to tell us like, oh, there's a lot of oxygen under us here, or oh gosh, there's a lot of carbon under us here. And it'll also be able to look at some of the trace elements that we're interested in. That's going to be really great because using the drill and using the mass spectrometer are very energy intensive. They use up things that are consumable. So once we use them, they're gone. And so for that reason, we don't necessarily want to be using them constantly. And so Dragons is going to let us kind of give us a first guess when we land somewhere new of how similar or different that place is than the places that we have been before. So if we get there and our Dragons data is like identical to the last place that we were, and we drilled and did mass spec measurements the last place that we were, we might make the decision not to do that at that landing site and save it for a future landing site. And then DragMet is our geophysics and meteorology package. That's kind of a weird combination of things for a spacecraft instrument. But really what's happening is it's a whole bunch of different kinds of sensors that share a brain. So there's a seismometer, there's a methane sensor, there's a hydrogen sensor, temperature, pressure, wind speed, like all of those kinds of things that will help us characterize the atmosphere and also help us characterize the near surface are all in part of DragMet. And then finally, our last instrument, which is again kind of a suite of instruments, is DragonCam, which is all of our cameras. And we have a bunch of cameras. We have cameras that are going to take imaging while we're flying and help us navigate. We even have like all the way down to like kind of microscopic imagers that are going to image kind of the tailings when we drill. Because we don't want to ingest anything sticky into the instrument because we don't want to clog it. And so before we actually ingest any material, we'll look at what did it look like while we were drilling? Like, does it look like it's a nice fine powder or does it look like gunk that we don't want to put into the instrument? So those are the instruments that we have. I'm going to skip a bunch of slides. Let's see. I'm skipping all of these slides. Okay. Because I want to make sure that we have a little bit of time for questions. So I'm just going to, we'll see. It's always a little bit of an adventure to see if a video will play. Oop. Well, it normally works. There we go. So this is a animation of the absolute most scariest day of my whole entire life. So when we get to Titan, we descend on parachute until we're about 1 kilometer above the surface. And then we get to find out whether or not we are actually capable of flying. So again, scariest day of my life. It's weird to know like a decade ahead of time when the scariest day of your life is going to be, but here we are. Once we land, at our initial landing site, we'll actually spend a good bit of time there. I'm going to pause this in one, maybe going to pause this in 1 second. There we go. So we'll spend a lot of time at our initial landing site, basically doing checkout. So we'll have to turn all the instruments on, make sure that they're working, make sure that the rotors are all doing what they're supposed to be doing, all of that stuff. And so our first landing site is probably where we will spend the most time of the mission, except of course except our last landing site, which is where we will absolutely spend the most time. And then once we're done at a landing site, we will, kind of pack up the car and fly off to our next landing site based on what I assume will be very heated discussions within the science team about where we're going to go land next. The reason that I paused it, though, is I wanted to point out a couple of things about Dragonfly, the spacecraft itself. So we do not have a fleet of orbiters around Titan like we do at Mars. In fact, we have 0 orbiters at Titan. And so we can't use any of those for communication relay. That means that we have to talk directly to Earth to send our data back. And so to do that, we have a high gain antenna. That's the kind of circle disc that's like on top of, if you think of like Dragonfly as having a head, it's the circle disc that's kind of sitting on top. It's gimbaled, and so it flattens out, which you'll see in a second in this animation. It flattens out to fly. And so that's how we get all of our data back. And then just a couple of other like trivia things, I guess. Dragonfly is about 10 feet wide and about 5-ish feet tall. So it's approximately 1 Sarah tall, actually. It's a very useful unit, but you aren't seeing me in real life, so that doesn't help. I'm 5'4". I'm about as tall as Dragonfly. So we're about the size of a small car. We're actually very similar in size and mass to the Curiosity and Perseverance rovers on Mars, which again are kind of the size of like a compact car here on Earth, just to give you a sense of scale. I'm trying to think what other things I always forget to tell people. I think that was it. So I will let Dragonfly finish trying to take off. So it's going to stow its high gain antenna, and then it's going to take off and fly. One other thing that's really cool, and you can kind of see this in this image, we expect that when the rotors engage when we're near the surface, that will cause some of the sand-sized particles to actually move, just as they do with a helicopter on Earth. And so we even will have the capability to actually hover and kind of create our own wind tunnel to study how the particles move on the surface, which is something that people are really interested in. And then finally, my last slide, and then if there's questions that people have, I would love to answer them. There are 2 fantastic books. If you have fallen in love with Titan over the last like 45 minutes, there are 2 fantastic books. They're both written by Ralph Lorenz, who is, we call him like the architect of Dragonfly. But basically, Lifting Titan's Veil is all about Cassini, the science that led to Cassini getting selected and developed, and then how Cassini got built and all of those things. And then Titan Unveiled was written a few years into the Cassini mission. And so it's all about like everything we learned about Titan that I summarized in like 3 minutes earlier from Cassini. They're both fantastic books. Ralph does not pay me to shill his books. He probably should, but they're both really great. And so if you want to know more about Titan, you should check those out. I also need to update this slide. I'm not on Twitter anymore. But I am on Blue Sky, if you know what that is, and my handle is the same. So I'm Planet Doctor on Blue Sky. I don't post much about Titan these days, but you can find me there. And also, if you have any questions about Titan tonight or a month from now or whatever, feel free to shoot me an email. My email address is down there. I will warn you ahead of time that I will reply to your email either in 30 seconds or like a year. But I will eventually reply to it, I promise. It just might be a really long time. In particular, it depends on how hard the question is that you ask me. If you ask me a very simple question, you will get a very quick answer. And if you ask me a more complicated question, you will get a longer answer, which will take more time. And with that, I would love to take questions if people have them.
Okay, well, I'm getting the microphone to somebody. I do want to ask, probably the question that we all want to know is that financially, the mission is safe?
Yeah, this is getting to be a harder and harder question to answer over time. So excuse me if I cry while I answer this question. We do not know what's going to happen with NASA funding right now. If you're paying attention to this at all, you would know that the House Budget Subcommittee provided their markup yesterday. It's not as good news for us as the Senate bill was, but they're both much better than the president's budget request. The worst case scenario I think that we are all kind of operating off of right now is the president's budget request. In the president's budget request, Dragonfly is safe. The reason that I'm emotional about that is twofold, I guess, because I love Dragonfly. If the president's budget is enacted, 41 NASA missions get canceled. Both missions that are operational, so missions like Juno, and some of the Mars missions, New Horizons gets canceled, and also missions that are currently in formulation, like Da Vinci to Venus and Veritas to Venus. In addition to Dragonfly, which is my main spacecraft love, which hopefully came through, I am also co-investigator on Da Vinci. We have undergraduate students here at Johns Hopkins who are building an instrument to measure oxygen on Venus. And if the president's budget is enacted, Da Vinci gets canceled. So this is a very hard time for our community. I'm sure that you're all very aware of that. We have lost a lot of people. It's been in the news recently that something like 2,000 NASA employees have already made known that they are leaving NASA. We have lost scientists and engineers on Dragonfly already. So even though the mission itself is safe, we have lost already colleagues and expect to lose more colleagues. And so it's a very hard time, but we are as safe as we can be right now. We are past a very major milestone in NASA mission life cycle, which is called the Key Decision Point C, or confirmation. Once a mission is confirmed, it becomes much harder to cancel. You get dragged like in front of Congress and have to explain yourself and stuff. It's not something that NASA can just do unilaterally. And so we passed confirmation spring of last year, which puts us in a much better position developmentally than the rest of the missions that have not yet left Earth. So that is a very long answer to your question, but I think it's important for people to be aware of what has been going on.
Thank you.
Now ask me happier questions. I can also see the questions online if you want me to just like go through those real fast. Up to you.
Thank you very much for your presentation. My question is, earlier this year we had a presentation about from NASA about how they try to prevent cross-contamination. So and it just kind of ties in a little bit, right? So as you're going from one place to another and you're drilling, how do you ensure that there's nothing left on, for example, the drill bit when you go to the second or third place, that you're starting from clean or scratch?
Yeah. Sorry, I had to move for a second. My laptop was about to die. That is not the question that I thought you were going to ask at the beginning, but that is a very excellent question. This is something that we worry about a lot, as you can probably imagine. And so there's been a lot of work done on that. And so basically, like, that's one of the big engineering challenges, actually, is figuring out, like, we spent a lot of time discussing, like, what level of contamination we would consider to be acceptable. And then, you know, then we take that to the engineers and say, okay, like, this is the level that we consider to be acceptable. Please solve our problem for us. Engineers love scientists on NASA missions, by the way. It's a really, really great relationship. Everybody gets along super well. We definitely don't have conflicting goals. But basically, it was a lot of conversations. And so the way that the drill is designed, a lot of the material that gets ingested actually doesn't end up getting used. But we have a lot of material, and so the idea there is effectively to kind of overwhelm whatever might be left in the kind of drilling mechanism and the way that it works. And then I didn't talk about DRAMs at all, but what happens is the material gets ingested and it gets put in a sample cup, and those sample cups are single use. And one of the reasons that the sample cups are single use is because of this issue with contamination.
What is the power source that's going to be running Dragonfly?
Yeah, so Dragonfly, that was not the direction I wanted to go. I'm gonna let this run for a sec so that I can pause it and show you. Dragonfly uses a radioisotope thermonuclear generator, so an RTG, just like Curiosity and Perseverance, New Horizons, Voyager. You can see it here. So this, I'm acting as if you can all see my pointer, which you definitely can't. But the thing that looks like a can, like somebody just stuck a giant can on Dragonfly's butt, basically, that whole can thing is the RTG. And so that's our power supply. So our RTG trickle charges a battery. Dragonfly is effectively actually a giant flying battery. In terms of mass and volume, we are a battery, basically. The instruments are just kind of like an extra thought, like stuck in some places to do the science. And so that's actually one of our limiting factors. Most of the things that we do are very energy intensive. You can imagine that flying is very energy intensive. Our mass spectrometer is also energy intensive. So the vast majority of Dragonfly's mission is sitting on the surface, charging its battery, and doing nothing else. Within these little spurts of, kind of frantic activity, and then going back to charging, which I think is like a little bit like a baby, like spends most of its time sleeping, and then when it's awake, it's, kind of crazy.
Thank you for the presentation. It's been great. I was curious, some of these graphics that you've shown demonstrate really interesting topography. You talked about dunes and interdunes and erosional features and so forth. How well do we have the surface of Titan mapped such that when Dragonfly is zipping around up there, will it be able to understand its own altitude, like with an altimeter, or like how will it know if it's going to crash into a dune or fly off down a valley and so forth? How well do we have that topography mapped?
Yeah, that's a great question. And somebody else in the chat, so I'm going to answer two questions at once, because someone else in the chat asked about how Dragonfly knows where to land and if it has autonomous capabilities. So I'm going to answer these two questions at the same time. So the first answer to your question about how well we know the surface is effectively like not. We know very little about the surface, which is one of the reasons why this mission is going to be so interesting, but also mildly terrifying. So this is why, again, we go to the inner dunes region. We're using the laws of physics and our understanding of dunes from Earth and Mars and Venus to find us our first safe landing site. After that, and I skipped this slide, we're basically going to be using this like leapfrog approach. So after our initial landing, we're never going to land somewhere that we haven't already imaged. So what's going to happen is we're going to fly. We're going to fly further than we actually want to fly on a given day, and we're going to image the area in front of us. And then we're going to fly back to a place we've already imaged, land there. That's our new landing site. Meanwhile, that gives the team the time to look at all the new imaging data and decide where our next landing site is going to be. That is also how Dragonfly is going to navigate. So Dragonfly is going to navigate, and this is answering the other question about autonomy. Dragonfly is going to navigate using something called terrain and relative navigation. We don't have a GPS system. We don't have great imaging data. And so Dragonfly is going to have to use the information that it has acquired about Titan to navigate. Terrain relative navigation is not new, but it has never been used in this way before. So the two newest Mars rovers, Curiosity and Perseverance, both use terrain relative navigation for the very, very last like moments of the decision making that those spacecraft had on board to make the final decision about where to land. And so it's already, that type of software has already flown. Obviously, we are extending its capabilities. That's undergone a lot of testing. But the one-way light time between Earth and Saturn, on average, is about 90 minutes. So we will not be in conversation with Dragonfly while it is doing things. It will have a sequence uploaded. It will have a goal in mind. It has all of the different logic depending on what things it sees happening. It will have the ability to, you know, abort flying and land immediately, or abort flying and land when it thinks is safe, depending on what has happened. But all of that will be pre-programmed, and every day is going to be an adventure.
Wonderful, thank you. I had a question on, you said that this is direct to Earth communication, that since there's not a orbiter, what sort of infrastructure do you have for receiving those signals? How, obviously we're not always pointed, either a place on Earth or a place on Titan would always be pointed toward each other. How does that work?
Yeah, so we'll be going through the Deep Space Network, just like the rest of the Deep Space NASA missions. And so the way the Deep Space Network is set up, there's always, basically you can always see two antennas on Earth. So they're Madrid, Canberra, and Goldstone. I was like, where's the US one? And so we'll be communicating through the Deep Space Network, and, you know, have already had the negotiations about having time on the Deep Space Network in like 2035, which is crazy, but here we are. And the other thing actually, just to mention, is that a really like lot of the time, we will not be able to talk to Dragonfly. So Titan is tidally locked to Saturn. And so there's long portions of time where we literally cannot see Dragonfly from Earth. And so that's fine. Like I mentioned, Dragonfly needs to charge its battery a lot, and so that actually works out pretty well, and it will make being on the science team a lot more sane than like on a Mars rover, because we're not going to be telling it to do new science things every single day. We're going to be telling it to do new science things every few weeks, and in between that, it's going to be sleeping while we do not have the ability to talk to it anyway.
I have a question. You said that the temperature was 94 Kelvin. Maybe I got this wrong, but isn't that 200 degrees below zero?
Someone else put that in the chat, that it's negative 290 Fahrenheit. Yeah.
How are you going to fly, and how are you going to keep the batteries warm? And, you know, I mean, 200 degrees below zero, how are you going to keep everything running?
Yeah, so the thermal is actually a really interesting situation. When you use an RTG, it generates a lot of waste heat. And so we actually have more issues in a lot of ways keeping the spacecraft cool enough than having to worry about keeping the spacecraft warm enough. But there is a lot of effort that has gone into the thermal system for Dragonfly. And one of the reasons for that is that when you heat organics in liquid, you make chemistry happen. We don't want to do extra chemistry with the spacecraft. We want to measure what Titan did. And so the way that the whole drill and mass spectrometer system is set up keeps those samples at the temperature they were sampled at through most of the process of the drilling and the measurements and all of those things, which was, I will say, like, I have so much respect for the engineers on this mission, because we have asked them to do like a million impossible things, and they just are like, okay, I guess we'll have to figure out how to do a million possible things. And they've done all of them. But it's definitely an interesting thermal challenge, especially because Titan's atmosphere is so thick. It's definitely a really challenging thermal environment. And there's like lots of other things you have to worry about too, like, you know, what lubricants do at 94 Kelvin and all that kind of stuff to make sure that the rotors are working correctly, and like all of these things that I'm glad someone else gets paid to worry about so that I don't have to.
Couple of quick questions.
Number one, what's the planned launch date and transit time? And how do you determine the mass of the moon Titan and the other moons?
Yeah. So the masses come from Kepler's laws, which is cool. So we're able to just like use pretty simple physics to figure those things out. It's really helpful when objects are orbiting each other because then you can use really simple physics to figure out how much they weigh. It's really annoying when planets don't have moons because it makes it a lot harder to measure things. I already got distracted. Oh, launch date. Yeah. So we launch, our launch window opens on July 5th of 2028. Which is a little under 3 years from now, which is bananas to me because I feel like we just started working on this mission 1 minute ago, which is apparently not true. We are, how does that math work? We're basically 6 years in cruise. So we arrive at Titan in 2034. Our mission, our nominal mission, so the thing that NASA has promised us in exchange for science is about 2.5 years. But assuming that NASA still exists in 2034 and they have some extra money when we're done, we would be able to go into extended mission like many other NASA missions have. At some point, our limit in terms of the lifetime of the mission will be the RTG because at some point we will not be generating enough power to keep ourselves alive, basically to keep ourselves warm enough, to keep the instruments running, to do all of those things. We'll lose the ability to fly before we lose the ability to do other stuff. So at some point we may end up just being a stationary spacecraft that's doing like weather measurements or something like that. But 2.5 years at least. So going into the kind of mid to late 2030s, we'll be doing science on Titan.
I had one question about Titan itself, then one for the Dragonfly. So about Titan, why is it so cold despite having such a thick atmosphere of like so many greenhouse gases? Like you would expect it to be at least a little bit warm.
Yeah, so it's basically just because it's so far from the sun. But you're absolutely right. Titan does have a greenhouse effect. So Titan has about a 20 Kelvin greenhouse effect, so about a 20-degree greenhouse effect that is from the methane and from the thickness of the atmosphere. So it should be even colder than it actually is. And in fact, there's some ideas that if there was no methane in Titan's atmosphere, the atmosphere would actually collapse because it would get too cold to be able to actually be in the gas phase. And so that greenhouse effect is actually something that makes Titan really interesting, but it's very far from the sun. So Titan only gets about 10% of the sunlight that the Earth gets.
Then the question about the Dragonfly is, since this is like the first object that has like an active atmosphere, and because the atmosphere is like organic molecules, like what is y'all's like worry about like having dust build up and especially like having big, heavy organic molecules on it?
Yeah, that's a great question. We do worry about that. So if you remember the experiments that I mentioned that we do, in addition to doing science with those materials as part of the mission, we actually also work with engineers. And so they use some of our materials as some of the tests to kind of see like, do we need to put special coatings on the windows? So that's one thing that's a big concern because we use our cameras for navigation. If they get gunked up, then it's going to be very hard for us to navigate when we fly because we're not going to be able to see things. And so that is definitely something that people have taken into consideration. One other thing that's kind of related to that I didn't mention, so I said a few times that it rains on Titan, that there's clouds and those kinds of things. We're landing at the equator, so Cell Crater is very close to the equator. And we're landing at a very similar time in Titan's season. So Titan's year is about 30 Earth years. And if you do the math, you will very quickly discover that we are arriving at Titan 30 Earth years from the last time we arrived at Titan. And so the Huygens probe landed near the equator in 2004. We're going to land near the equator in 2034. So we know a lot about what the weather on Titan is like during that particular period of its seasons. And in general, as far as we can tell, that period of time, it does not rain, it doesn't really storm. And so we don't have a lot of concerns about weather causing us issues when we fly. But of course, as any good pilot would, we will do a pre-flight weather check And if it seems like something bad is about to happen, Dragonfly will not take off. It will be like, sorry kids, like we're not doing this today. We're not gonna go fly into a rainstorm. We have self-preservation instincts. And so we do definitely like worry about things like that. We do not want liquid methane on the spacecraft while we're flying. That is not, we don't want that to happen.
We got time for one more question. Does anybody have a question?
I did a presentation for a group a while back about the New Horizons mission, and in researching that, one of the things that really struck me was how the things in the solar system are a product of their place. And I just listening to this, it just made me wonder what range in the solar system could Titan exist as the way Titan is right now? I mean, like Titan is bigger than Mercury, but unless you put it where Mercury was at, and then it would evaporate.
Yeah, that's a great question. People think about that a lot in a little bit of a different context because there's been a lot of conversation about what it will be like on Titan when the sun becomes a red giant. So it might actually be a quite pleasant place in terms of temperature when the sun goes red giant. But it's definitely, I mean, I think a lot of these things are Goldilocks, and you can think about Earth in the same way. You know, we're very close to the triple point of methane, and so that's kind of finicky, the same way that Earth is very close to the triple point of water, which is also kind of finicky. So you change the conditions just a little bit, you end up with a completely different planet. And I mentioned that Titan and Ganymede are the same size. Size tends to be one of the things that determines whether or not a planet has an atmosphere. And so the fact that Titan has an atmosphere and Ganymede doesn't is very weird. One of the possible explanations for that has to do with the way that we think that the large planets in the solar system migrated early in solar system history. It's very possible that Ganymede just got too close to the sun when Jupiter and Saturn were migrating, and that at some point it maybe did have an atmosphere and it got too hot and it lost it.
So thank you so much for taking your time to speak with us, to speak to us. We hope the best for the mission, the future of the mission, and it's just been a fascinating presentation and just delightful to hear from you about this. Thank you so much.
Thank you. Thank you so much for having me.
Okay, so it's break time, so in 10 minutes we'll come back around and watch your eyes.
umbrella here with the Milky Way galaxy printed on it. Several interesting books ranging. What's that? Oh, the timing is right with the rainstorms this evening. Plus, the other highlighted thing is you can take your field notes in this nice spiral notebook. And so here we go. The first number for tonight is 480-6496. 480-6496. Come on up. Claim your prize. When I was growing up, our church group would go to what we called the old folks' home and play bingo. And we would call two numbers and someone would yell, bingo. It happened frequently. It was one of those life lessons that you walk away with. 480-6519. 480-6519. Okay, Tom, come on down. And so while he's making his choice, let's move things along and call the next number, 480-6508. Thanks. So good. Okay, thank you. Okay. 480-6492. 480-6492. All right. And let's keep going. 480-6476. Come on down, Ted. The next number, 480-6490. 6490. No one? No one? And the last one, 480-6506. 480-6506. Yep. Thank you. Okay, great. So just muscle your way in there and find something that you need. And I'm going to turn it over to our next speaker, Mr. Hall.
Thanks, man. You can't stand there anymore. You can't stand there anymore. There you go. You need a book about the road to reality. So now I'm going to talk about what's going on next month in the sky. This one, Glenn Fraser took this. It's some object called CTB1. I've never even heard of the catalog before, but it's beautiful. Go to the next slide here. Kind of reminds me of the Abell catalog. Got the next slide going on? Oh, sorry. Forgot to do that. How's that? All right, yeah. Beautiful. Next slide. All right, well, speaking of Titan, to continue our theme this evening, Titan continues to do shadow transits across the face of Saturn. We've got 3 of them coming up this next month, and as you can see, it's getting, hey, go back. as you can see, it's getting earlier and earlier in the night, and you'll have to take my word for that. Occultations and close approaches. We've got the moon and M45 pretty darn close here. And Saturn and Neptune, it's a little over a degree, but thought I'd throw that one in because that's kind of cool. And moon and M45 again, and Venus and Jupiter, about half a degree, and then moon and 45 again. This is John McCrae's image of the moon and Jupiter conjunction. You can see the little moon, one of the little moons there. Next slide. It's about as new moon as you can get, right? This is Patrick McMahon's picture of the last eclipse last year. Our next new moon is on July 24th. Hey, Meg, settle. Next new moon's on July 24th. Next slide. Venus is at its highest, it's morning star, 34 degrees up in the sky on July 26th and shining at negative 4.3. Next slide. So one of the 2 meteor showers that's going on this next month, this is the first one, it's Delta Aquarids. It's right in Aquarius right here. This is the radius. It's debris left behind by a 96P Mach-Holtz, and it's not a heavy one. It's about 15 to 20 at its greatest when the radiant is highest in the sky. But we've got a 19.6% waxing crescent moon that sets at just a little before 11 p.m. on the 28th of July. So it's favorable for what meteors it yields. Next slide. Oh yeah, and then there's the other meteor shower. You've heard of this one maybe. The Perseids. Once again, August 12th, as always, it's the big peak night. You know, the 60 ZHR is kind of always what I consider to be a bit of a conservative figure. Sometimes you see 120, sometimes you see 60, sometimes you see 100. This is not the best situation because we've got an 84% waning gibbous that rises at 10:22 p.m. The night of the 12th, but still worthwhile. We know how bright these meteors can be. And this is material from 109P Swift Tuttle. Next slide. And we got full moon on Saturday, August 9th. This is Robert Cargill's beautiful picture of the moon. Nice detail there. Next slide. Pallas opposition. So the second asteroid to be discovered is going to be at its closest to us, opposite of the sun from the Earth, on August 9th. And it's going to be magnitude 9.4 in Delphinius. And interestingly, you don't think about the asteroid belt asteroids not being on the elliptic plane, but this is actually a rather high orbit. This is the orbit of this is actually 34.8 degrees off of the ecliptic here, and it's the largest known object in our solar system not to be rounded by its own gravity. And that little round nugget in Dr. Horst's picture there that showed all the non-planets that are round. That is the only one that's actually round-shaped, but isn't rounded by its own mass. Next slide. And Mercury in the morning. So we got greatest western elongation on August 19th. And Mercury will be 17 degrees above the horizon, so a little bit higher than it has been in its last visits to the highest in the sky at magnitude negative 0.2. Next slide. So, as for last month, you gave me license to start talking about southern constellations. So thank you for that. You're going to hear about stuff that you've probably, some of the stuff you've heard about before, and some of the stuff is like brand new. But it's all really cool because everything going on in the southern constellation, just because it's not in our sky, doesn't mean it's just as amazing as what's going on up here. So we got Dorado, the dolphin fish. Dorado's rooted in the name. Dorado is, means gold. And so originally the idea of this was that Dorado was a goldfish or a swordfish. And I guess over the years, they just settled on tuna because that's really what a dolphin fish is. It's basically a maui-maui. So it was created by Dutch astronomer Petrus Plancius, and it actually first appeared on his globe. And when they were doing, like star chart people back then, it was not always like in a book or on a flat piece of paper. Sometimes they were issuing a globe. It's got 2 stars with known planets, and it's got one particularly nearby galaxy. Next slide. So, let's talk about this star, HE, and then these numbers right here. This is a star nobody's ever heard of, or maybe you have, probably not. But by its trajectory, it's basically thought to have been a triple star system that moved through the center of the Milky Way galaxy and was affected by the gravity of Sagittarius A star, our central black hole, messed up the triple star system. Who knows what happened to the third one, but that 2 of the stars basically merged, and the gravity, basically a gravity assist, basically, threw this thing to a trajectory on a speed that's 3 times faster than the speed of our sun is orbiting around the Milky Way, and basically ejecting it out of the galaxy. It's actually moving at a speed that is higher than the gravity, what do you call it, escape velocity. So that's it right there. Bye-bye. Next slide. So what's this big red thing? Well, this is the galaxy that I was talking about. I've been down to Chile and I've seen this thing with my own eyes, and it's the most amazing thing to be standing there and looking up in the sky and seeing a galaxy. I mean, like, what galaxies do we have to see here with our naked eye, or the little tiny faint fuzzies of M33 and M31 when it's dark enough? But this thing is crazy bright. It is big. It has got the, well, it'll come up in a second, but it's got a nice magnitude to it. Even though it's spread out over the entire galaxy, which means that it's dimmer than what you'd think that magnitude implies, it's still bright, certainly naked eye, and you're looking at a galaxy. So it is the 3rd closest to the Milky Way, 3rd only to the Sagittarius dwarf and the Canis Minor dwarf. And it's got about 60 globulars, 400 planetary nebula, and about 700 open clusters. So actually doing science and observation about what's going on in another galaxy that's right up next to us like this, it's just a hotbed of observation and cool stuff to look at. It's the 4th largest galaxy in the group. We've got what? Andromeda. We've got Milky Way. We've got the Triangulum Galaxy M33, and number 4 is the Large Magellanic Cloud. It's called the Magellanic Cloud because Ferdinand Magellan, in his adventures down in the southern hemisphere. In his writings about the trip, that's just, everybody was like, well, okay, well, it's your galaxy. We're just going to use your name for that. So next slide. And this is it. Just beautiful. Next slide. So this is all the goodies that are in the Large Magellanic Cloud. So I decided to pick Dorado first because it housed the Large Magellanic Cloud. Actually, most of it is in Dorado. There's some of it in Mensa. There's some of it in Volans, and some of it in another constellation I can't remember. But you've got a ton of NGC catalog stuff, and you've got just a ton of nebulae, and I will talk about the ones that start with N. This is actually a catalog that's specific to the Magellanic Clouds that I'll talk about in a second. Next slide. The Tarantula Nebula. I'm sure everybody's heard about that before. If the Tarantula Nebula was as close to us as the Orion Nebula is, it would cast shadows. It's that bright. It lives in the Large Magellanic Cloud. It's the largest and most active star-forming region in the local group. Now we're talking about all the galaxies that are bound by gravity in our galactic group. So that's actually a pretty significant statistic right there. Near center, if you're going to go to the next slide, near center is an open star cluster, and that's pretty much the powerhouse that basically illuminates this whole thing. So that's the Tarantula. Next, yes, sir. Oh, yeah. Oh, yes, absolutely comparable to like the Orion Nebula. Yeah, you can see it with your naked eye. Yeah. So next slide. Oh, go back. This is cool. I don't think I paid attention to this. I don't know how, but Alsace Observatory is where I was to see the eclipse. So it's crazy that the picture is like, it's where I saw the Tarantula was. It's the same place where this is taken. It's cool. All right, next slide. NGC 1850. So this is also in the Large Magellanic Cloud. This star cluster is a weird one. So it's structured like a globular cluster, but it's got new stars in it. And that is absolutely the opposite of a regular globular cluster. Globular clusters are made of old ancient stars. Some of them we're talking about the age that's, nearer to the age of the universe than not. And so what has been identified with this particular cluster is that it's very much near, and if you want to go to the next slide here, it's very much near a great deal of gas. And because of the gravitational pull of the star cluster and the density of the star cluster, it's pulled gas in and actually created starburst formation. So that's how they've identified why a globular has new stars in it. So kind of a space oddity here. Next slide. And then there's the N44 super bubble complex. So it's the big name like the Ophiuchus cloud complex. It's the big name down there. So it's the N catalog. So Carl Heinz, it's a catalog of hydrogen alpha emission stars and nebulae in the Magellanic Clouds. So anything that starts with an N is going to be for nebulae, and anything that starts with an S is going to be a star. So there's actually, go to the next slide here, really hot blue stars basically carved out this bubble right here just from intense stellar winds. And there's another bubble that's inside of it. I think it's this guy right here that is created by the same mechanism there. So and it's huge. I mean, we're talking about 30 minutes by 30 minutes. Next slide. And there's supernova 1987A. So this is a blue supergiant that went supernova. And up to a certain point, the astronomy world did not identify blue supergiants because of their density and age, that there was any sort of, or temperature, that there was any sort of way that a blue supergiant could actually become a supernova. And there's speculation that one of the cause is that it was the merging of two stars to actually give the supernova, or give that progenitor star the thing that it needed to actually implode and explode as the supernova. And so that's the supernova remnant right there that is growing. So remember, the light reached us in 1987, okay? Next slide. This is the little nugget that's in the middle right here. Okay? That's what, 30 years after the supernova, 35 years after the supernova, whatever, 1987 to now is, whatever. Do the math yourself. So if anybody needs to understand some modern nomenclature about the word sick, this next slide is sick. Next slide. They did a time lapse over a 30-year span after the explosion. So this ring right here is basically just a ring of gas that's around the progenitor star. And when the star exploded, it just lit it up. That's all just ionized gas at that point. And it's just getting it's just getting hit by all the stellar winds from the explosion. Crazy, huh? Next slide. NGC 1566, I could not do. We can talk about the Large Magellanic Cloud all day long, but cannot do a constellation without having a spiral galaxy featured. So this is called, go to the next slide, this is called the Spanish Dancer Galaxy. Beautiful spiral. It's one of the closest and the brightest Seyfert galaxies. Seyfert galaxy is basically a galaxy where at its core, it's got a quasar-like emission from it. And at certain other wavelengths, not visible, but at other wavelengths, the core itself is brighter than the entire Milky Way's light emission. Next slide. So this is all the stuff where I got stuff. I have all my sources here, Wikipedia and sciencenasa.gov. But I suggest that you Google the HE and then those numbers there, that star that got cast away. There's so much more to the story, and it's actually very, very cool. More information about it, and about supernova 1987A, and then the science behind it at scisimple.com is like a really killer site that speaks to that. And that's let's see, next slide. So this is Corey Morris's image of IC 1396, which contains a little elephant right there. And keep looking up. Thank you.
Fantastic. Thank you. Okay, so we're going to go to the business meeting, and Constantine is up with the financial report.
Thank you, Bruce. Well, good evening, everyone. As you can see, our current balance is $43,669, and over this past month, we've received a little over $3,300, primarily from membership renewals. We also spent a little over $2,200, the largest part of which was our Astronomical League membership. If we move to the bottom half of the page, as you can see, our current balance for Rising Star is $3,000, and our next payment is due in October. Any questions about the report? Okay, let me go ahead and talk a little bit about membership. So as of July 6th, we have 173 members that have renewed out of 234 that we started with. So we've had a significant drop. It's still July, and those individuals will not be removed from the books until the end of July. So if you're here and you haven't renewed, please do so. Also, reach out to your friends that are members and check and see if they've renewed. If not, ask them to renew. Our total income from the renewals is $9,410. And to make you feel a little bit better about the losses, take a look at the bottom half there where it talks about the percent renewed historically. Right now we're at 74%. In 2023 it was 75. So any comments or thoughts about this or questions? I'm hopeful that we'll get at least a few more members, but it's been pretty quiet the last couple of weeks. Thank you.
Thank you, Constantine.
Oh, I have a quick question. For years, we've been talking back and forth about Nolan renewal. Are we yes, no, or forget about it?
Well, that is certainly something that I, as a treasurer, would love for us to do for a number of reasons, but it is going to take some concerted effort by the treasurer as well as membership, and we just don't have the volunteers we need to make that happen as of yet. So I personally will continue to pursue it, and hopefully we can make that happen in the next couple of years.
Any other questions for the treasurer? All right, let's move to the executive board updates. I guess these are mine. Let's go to the next slide. So at the board meeting last week, we formed a temporary committee called the Noble Observatory Operations Committee. And the goal of this committee is to assist Robert Circus in his endeavor to get the Noble up and running. So we've got a team in place now. You can see the committee members down here that are going to provide the knowledge and horsepower to get us across that finish line so we can get the Noble Observatory up and running. You can see the mission of the committee to continue on the good work that Robert has done and then get the observatory up and running, and so it's available to all of us. Let's go to the next slide. So I just want to bring a note up about how we're going to manage the Zoom meetings going forward. For those of you that read the emails, there was an issue when Night Sky Network did the premiere screening of Sally. Their event was interrupted by a bad actor who published offensive material. And the board realizes that if it could happen to the Night Sky Network, it could happen to us. So we are going to take defensive measures where we're going to do what we can to prevent such attack. We're going through the options that are available to us now, and you'll be informed of them. So if you do participate via Zoom, you will know what actions you need to take to participate in the near future. Let's go to the next slide. And now we're going to get an update from Cy on the bylaw changes.
How you doing? Next slide. Oh, there it is. Thank you. Yeah, so on the committee, we started this about almost 2 years ago. Chris Ashford, Stephen Kennedy, Dennis Webb, Ted Smith, myself. We went through the bylaws extensively. It's been a long time going through there. We made some proposed changes to the executive board at the May board meeting. And if you looked at the Prime Focus, we had the changes in the Prime Focus that was published right around July 1st, and about 2 days later, that's right, 2 days later I sent out an email with the links. Next slide. These links, there was one copy has all the changes. You can see all the additions, back, subtractions, comments, and such. And then the bottom part was the final copy. Next slide. So here's kind of the rules that we're going through and what we tried to accomplish while we were going through it. We tried to remove inconsistent terms, group similar functions together, incorporate how we actually been working since we incorporated the bylaws, 20-some years ago. And the goal was to try and make us a more professional organization. We also separated the appointed positions from the elected positions. So now in Article 3 in governance, it just talks about the officers and how we do elections and all that. And we moved all the appointed positions and committees down in Article 4, I'm sorry. We talked about how the bylaws should only list what we actually do and the powers, how we run the organization, all other operations, how we do star parties, all the rest of that stuff. We wanted to move out of there. We wanted to keep this a static document so that we don't keep changing it all the time. Like, okay, now we started leasing equipment, yada, yada. Now we're doing this. So we wanted to keep this so we don't have to change the bylaws so much. Next slide. All right, we moved all, but most, but not all references to specific online folders, like in a merchandise store, because then there was talking about, okay, we have a Cafe Press account. Well, now we have Zazzle. Well, we just changed that to online merchandise store. And instead of talking about Google's I.O. or Group's I.O., okay, that's our online discussion board. And as far as Google Docs and such, okay, that's our documents repository. So we tried to make that as generic as we could. We wanted to standardize the capitalization of stuff. This was brought up, and we kind of just talked about, okay, the directors, maybe in the future we'll have them do some duties, but we didn't really specify them, but we opened that up so there's possibility so that the board can actually do that in the future. When we talk about duties, we thought about these 4 things. We got our physical stuff. You know, we got our land, we got our equipment. We got our people, so we're talking about membership and training and all the rest of that stuff. And we have our outreach. So that was a different separate section we talked about. And then the 4th one would be social media. So we kind of looked at that, but that's something the board will figure out in the next year or so. We left that open. There we go. And then we incorporated some things since we've been through COVID on how we can vote online and actually have some virtual presence. Next slide. I'm sorry, go back one. I was confused. There was some confusion between membership. So membership just applies to individual membership or the family membership. And members are all the people that are part of that. So those terms were interchangeable throughout. We talked about membership meetings and member meetings, so we just changed all that to annual meetings or monthly meetings and such. So we clarified all that so it's a little more standard. Next, yes, thank you. All right, and there was some confusion between what are officers, what are board members, and what's the executive committee. So the officers only consist of 4 people: president, vice president, treasurer, and secretary. And then we had what we called open directors, which is always a confusing term to me. It's like it's open, like it's not filled. So we changed that term to managing directors. So we got our officers, we got our managing directors, and those 2 groups together are our executive board. So we changed all the language so that's consistent throughout. A couple other things we incorporated, swearing in officers. We actually did that last month. Changed, for instance, one of the things we changed was the Dark Sky Committee, the Observing Area Committee, and we did a lot of changes on, as far as the Observing Area Committee or all these other committees, what they actually do. And we did that with some of the officers, what we've been doing since we have taken the land over the last couple of years, and what do we actually do as far as inventories and all the rest of that. So it's really clean now. Next slide. Also added the appointed position of legal representative or representatives, and also gave us the ability to, in the bylaws, to hire outside legal counsel if we need to. Of course, that's got to go through a vote on how much money we're going to spend. But we thought that was important to put in there. We also include some language on fundraising and such. The reason for that is, okay, let's say the project we were just doing for the Dark Sky, we needed $5,000. We raised $5,100. Well, what do we do with the extra $100? Do we give it back to the last guy who donated? Do we do a pro rata share, refund back to everybody? So we put language in there. Okay, if we raise more than what we actually wanted, that money's going to go into the general fund for the future operation and administration of the project. So it made it a lot easier so you didn't have to do some more votes on what to do with the extra $2. All right, and then if you looked at the first document I talked about, so we got, there'd be strikeout, reds, strikeouts, additions in red, yellow highlights. So if you're looking through the document, you can actually see what we did. Any questions? We're going to vote on this next month. Any questions on that? Bruce, you're up.
Did you tell them where they can find the document?
Oh, yeah. If you want to go back 3 slides. One more, I'm sorry. And that was in the email I sent 2 weeks ago. You actually see that's the slide with all the markups, and that's actually the copy, the hard copy of what it's going to look like at the end with all the changes. All right?
And so we don't have any business tonight that we need to vote on. We'll just have, this is our time where we make available to you the changes of the bylaws. And are we going to do the motion today? No. Yeah, skip that slide. So we made available to you the documents that Cy described, and they're available out on Groups.io. We encourage you to go look at them, and over the next 30 days, and at our August meeting, we'll vote on the changes that we're being proposed, and then we'll discuss them, and then we'll vote on them. I think I said vote on them twice. We'll only vote on them once. The other business now is for anyone who wants to bring up any other business in the business meeting. Yes.
I want to thank you and your team for finishing the wall in your training room. I think it's an outstanding job, and it exceeded my expectations in what I wanted to accomplish out there, and I really appreciate it. And it's another reason for people to go out, because now you'll be able to camp out, chill, and all that kind of stuff. Thank you very much.
Good. So thank you, Bob. Let's move on to the next topic. And I believe these are the monthly reports, and the first are the announcements, and I have a few of those, so let's go. I just want to remind everybody that the club has reserved October 24th, 25th, and 26th at the Three Rivers Ranch. It has what you see in the picture is the large observing area that we'll have access to. On the far side, on the left side of the picture are the bunk rooms, and on the right side, are the cabins, and on the right side there are a couple of the bunk rooms that you can see. The club is we'll have total access to the observing field. We'll do a lottery to figure out who gets to sleep in the cabins, and then the bunk rooms will be made available, one for women and one for men. There are RV hookups there, and they do allow tent camping. I'd call it primitive tent camping, but that is an option. And then fortunately, we'll hire the 3RR volunteers to operate the campus scopes that'll be discussed in the next slide. So what I do now is make sure you put October 24th, 25th, and 26th on your calendar and plan to go. It's a Bortle 2 Sky. It's in the part of the, well, let me go through this. The Three Rivers Ranch is owned and operated by Texas Tech University now. It's a large property, and it's located in what they call the Big Empty. There's not very many people who live in this area, and there are very few lights and light domes. It's a great place to do visual observatory and to do astrophotography. To give you an idea how far away it is, it's about a 3-hour drive from this facility, so up near Wichita Falls. So we've got the site reserved for ourselves, and these are the scopes that will also be available for us to look through, a refractor and 2 large Dobbs, so it'll be very nice. And then we talked about that. So let's go to the next slide. Okay, we started this last month, and we did have some people stand up for the telescope service and repair job on the 2 Meade telescopes. Robert Cargill's going to refurbish one of them, and Tom Roth is going to do the other. So I appreciate to those folks for stepping up to get these scopes back into service. Let's go to the next slide. I did want to present another need that the group has. In our group's I.O., we need our admin, which was John. He relinquished that position, and George Lutch has been doing the job for a while, and what I like to do is get somebody else in place. And the idea, what you have to do to be the group's I.O. administrator is be part of the membership committee, and so you can add new club members to group's I.O. so they can join one of the groups. And then you also then have to remove people when people decide to leave the e-group or leave the club. If you're interested in volunteering, if this is in your sweet spot, contact me, and I'll get you the training you need to take over this position. Let's go to the next slide. So now we're to the monthly outreach part. So if you're going to give one of these presentations, why don't you start moving down this way? And Patrick, you're up.
All right, so this is summertime, so we got a real short one here. So we actually have two this coming Saturday. The first is the Space Day. It's our annual thing at the Fort Worth Museum of Science and History. There'll be several vendors. We're one invited, so it runs from 10 to 4. This is a great opportunity to promote our club, astronomy. So if you want to help out, even just for a little bit, just let me know or just show up. If you do volunteer, you'll be parking in the parking garage, and they will give you a voucher for that, so you don't have to pay for parking. And then later that night, we're going to do a star parade up at Fort Richardson State Park. I'm not sure what crowd to expect, but I know I've had a few people said they're interested in helping, and if you'd like to, feel free to come. Okay, next slide. And then next month we'll be back at Dinosaur Valley on the 16th. Thank you.
Well, we're going to try again on August the 2nd for our Tandy Hill Star Party. Right now, we're not doing very well this year. We got clouded out last month, as we have for most of the months this year. But anyway, it'll be August the 2nd, and the sun sets about 8:36, something like that. If it's clear, there'll be solar observing before. And what I always like to tell people is if you're new to the club, if you have a new telescope and need help in operating it or just looking for a telescope, come on out. We have all different types of telescopes you can test drive and see which one suits your purposes. So come on out on August the 2nd if it's not raining.
Very good, thank you. Next slide.
All right, we're looking to start the Young Astronomers again in this this fall. I'm still working on specific dates, and I'm working with Mike Sweat to maybe start one more in the Fort Worth area as well. So that's where we stand on Young Astronomers for now. We'll let you know. We got a new update.
Nothing going on at 1687. Again, it's summertime, it's hot, and the weather hasn't been helpful, and sunset and all that kind of stuff. I expect we'll pick up 3 or 4 starting September time frame. So that's all we got. Thanks.
Thank you. Okay, so the Cross Plains Public Library, I'll do that one. We do have a presentation for them this Saturday as well. It has to do with the how to observe a meteor shower. And this is, to highlight that, this is David Cox's picture of the radiant looking east. Unfortunately, the meteors don't pop, but it's a fantastic picture. So that's a go. We're going to go ahead and do that rain or shine. Next slide.
there's not a whole lot to report about the state park. Hopefully we're still at 2026 to open it up. Everything's under construction all at the same time, so it's a lot of buzzing out there. So then I can do a rising star report. Okay, so the OMG group, the Old Man's Group, added Ted Smith and Sam Morehouse, and along with Charlie Haggard and Bruce and myself, we've constructed the wall and we made doors out of the wall. It's kind of like Maine cabin masters. The floor's not even, the cargo container's been crushed, so at the waist it's 3 inches wider than it is at the bottom, and so we're all just like a lot of collaboration and everything, but we did the job. Everything fits nicely. There's 4 deadbolts on the east side and 3 on the west side. So there's total isolation. If you want a secure place to sleep, you have that choice. Both sides have to raise deadbolts to open the doors. There's deadbolts on the doors. We flanged the doors with the plywood, so there's no visual communication between the 2 sleeping quarters. That's bearing in mind our female population, that they would feel a little more secure staying out there. The group worked in hot weather, drank a lot of Gatorade, a lot of bananas, and just a lot of fit and fiddling. We got it done. It looks great. And thank you, Bob, for that. And thank you for all your hard work, too. So.
The Old Man's Group, boy, that's oh.
I'm sorry, I wanted to give thanks to Ted and Sam for joining the group because they added a lot of skill level to us. I want to be a very special thanks to Charlie Haggard. He's a quiet guy, but every time we go out and work, he outworks us, and he brings up ideas that we wouldn't think about. I learn every time I go out and work with him. So thank you very much, Charlie.
Okay, website and media report. Is George online?
I'm here.
Fantastic.
Not much to do report-wise today. Just let everybody know that if anybody is interested in publishing like equipment reviews or doing articles about current day astronomy events and such, please get in touch with me. If you have any suggestions about the website or the newsletter, also please get in touch with me. My email address is glutch@gmail.com. And I'm always interested in finding out new perspectives and views on putting new things into the the newsletter and the website. So let me know.
Thank you, George. Okay, so we have done an update to the website to highlight the Dinosaur Valley and the Tandy Hills Star Parties. And what web page is that on? Oh, okay, it has its own tab? It has its own tab. Okay, so we can direct the public to these events easier. Okay, fantastic. Thank you. So, Dr. Furio? So, good news, and Dr. Furio from UTA, yeah, I remember that now, is going to come over here and talk to us about binary star and brown dwarf development. I don't know what that means, but yeah, we will. Like, I didn't know much about Titan until tonight, so that's pretty cool. All right. And then the social house is still on the menu for tonight, so if you're interested, just work your way down there. And I think we're at the close of our meeting, so I would entertain a vote to dismiss. I mean, a motion to dismiss. And we have a motion and we have a second. So all those in favor, raise your hand. The motion carries. Thank you. Y'all have a safe drive home.